Hi, we'll now be looking at the concept of a quadratic expression. We've already seen the various concepts involved with quadratic equations. So we'll now be looking at the idea of a quadratic expression. What do we mean by a quadratic expression? We'll go on to discuss how to plot the graph of a quadratic expression. By plotting the graph of a quadratic expression, we'll also be able to talk about the solution of what are known as quadratic inequalities, which will then have their own applications, right? So let's start with the idea of a quadratic expression here. But before we go on to a quadratic expression, it turns out is basically a function of the variable. A quadratic expression in x is basically a function of the variable x. So we just quickly want to look at the idea of a function at a very, very basic level. Functions, of course, is something that we'll be looking at in a lot of detail once we start with calculus slightly later on. But for the time being, we'll be just looking at the idea of a function at a very basic level. For the time being, again, it is enough to understand that when we typically talk about a function of the variable x, we essentially are referring to an expression involving the variable x, whose value then depends on the value that x assumes. So, as an example, if I consider 2x minus 1. So, if I look at the expression 2x minus 1, this expression obviously is an expression whose value depends on the value of the variable x. So for example, when x is equal to 0, the expression's value is minus 1. When x is equal to 1, the expression's value is 1, and so on. You can give x infinite values, and in this case, for example, for each value of x, you'll get a corresponding unique value for the expression. So this, I'll say, is a function of the variable x. Right? So typically, a shorthand notation to talk about a function is something like this. So something like this will be read out as f of x. So 2x minus 1 is f of x. When I say f of x is 2x minus 1, so f of x over here is referring to a function of the variable x. You could have used some other letter instead of f also. So you could have said g of x or h of x. But again, the idea is that f of x is referring to a function of the variable x. And again, what you mean by this is that as x takes different values, the entire function will assume different values. So you can now talk about something like what would f of 0 be. So when I say f bracket 0, what this means is this denotes the function's value at x equal to 0, which in this case obviously is minus 1. Similarly, f of 2 would be the function's value at x equal to 2, etc. And it doesn't have, you could take some other values also. So f of minus half becomes right. So again, a function, when I talk about a function f of x, I'm essentially referring to an expression involving the variable x, and as x takes different values, the value that the expression takes will essentially depend on the value that x assumes. It is not necessary that the function's value will keep changing with x. So I could define something like this also. So when I say f of x equal to 2, when I'm talking about the function f of x equal to 2, I'm referring to what is known as a constant function. So here, the way you've defined the function, the value of the function essentially is not really depending on the value of the variable. As x takes different values, the expression's value remains the same. Typically, in the context of functions, you denote, typically in the context of functions, x is what is known as our independent variable. So by the independent variable, what we mean is that x is we are giving different values to the independent variable x, and the entire expression's value then changes depending on the way the function has been defined. So in the context of a function, we also usually introduce what is known as the dependent variable, which we usually represent by y. So when I write down something like y equal to f of x, so what I'm saying over here is that the variable y is a function of the variable x. Again, x is something which is the independent variable over here, and y is something which we define as the dependent variable. Right? So, and again, the reason why these terms are being used is that, by the dependent variable, essentially what you mean is that the value that the dependent variable assumes will depend on two things. It will first of all depend on the value of the independent variable, and at the same time it will also depend on this function f, right? So different functions, obviously for the same value of x, you'll get different values of y. So obviously, as in a simple example again, if you have y equal to x square and another function is y equal to x square plus 1, then for x equal to 0 over here y is 0, and for x equal to 0 y over here y is equal to 1. So typically the value of the dependent variable will depend again on two things: the value, the specific values that the independent variable is used, and the value and the structure of the function. The idea of a function as an input-output machine helps us understand a lot of concepts associated with functions. So let's just look at it. So we can imagine such a scenario in which, again, let's say we're talking about the function y equal to f of x. So in this case, we can think of a machine in which you maybe have a machine of sorts and you have this circuit over here. So the circuit essentially is the function f. The input to this machine is the independent variable x, and the output of this machine is the value y. Right? So x over here is the input, and y over here is the output. And f over here is the circuit of the machine of sorts, is the involved circuit. So one way of thinking about this whole function is that you have this machine in which the independent variable will act as the input. Then the circuit or the function over here, the machine over here, transforms, depending on how the circuit has been designed, how the function has been defined. The circuit or the function will transform this independent variable into some other value, and that value is then stored in the variable y, which is basically your output. So again, as an example again, when I talk about the function y equal to 2x minus 1. So in this case, I'll say that as the different examples that we've seen, so specifically when the input is 0, the output, I'll say over here happens to be minus 1. Right. So again, your independent variable is the input. The function is essentially the circuit which is transforming the input value, and whatever the output is, and again the output will, as we've discussed, depend on two essential things: the exact value of the input that has been given, and of course the way the function has been defined, or the kind of circuit that is there in the machine. And whatever the output is will be stored in the dependent variable y. One thing at this stage that again I would like to mention, and which will be emphasized in greater detail later on, is that it is not that any if I were to write down just any relation between x and y, then that will constitute a function. Basic requirement for a relation, a function of course is some relationship between y and x of sorts. It's a relation in which y and x are getting connected. But for that relation to categorize as a function, one basic requirement is that for one value, for a particular value of the input, for a particular value of x, there should be exactly one value of the output, right? So again, for one specific value of the input, there should be exactly one value for the output. So you don't want a situation in which you have one value for one given input, you have more than one possible outputs, right? There should not be any ambiguity over there. What is, however, allowed is that you can have a situation in which for different possible values of the input, you have the same value of the output. So let's see some simple examples. So for example, in this example, what is happening, it's pretty easy to see that for any given value of x, you'll get exactly one value for y. So for x equal to 0, you're getting y as minus 1. For x equal to 1, you'll get y as plus 1, and so on. Right? If I look at the example of y equal to x square, in case of y equal to x square, also this basic condition of course is getting satisfied, that for one specific value of x, you'll obviously get exactly one specific value for y. But what is also happening over here is that, for example, for x equal to 1, the output is 1, and even for x equal to minus 1, the output is 1. Right? So what's happening over here is that for two different values of the input, so again, what's happening over here is that for two different values of the input, you're getting the same value of the output. Something like this, of course, is allowed, right? As far in the definition of a function. An example of a relation between y and x which does not constitute a function would be something like this. Suppose I consider y squared equal to x, suppose I consider y square equal to x, where again x denotes the independent variable and y denotes the dependent variable. So if I take x as the independent variable over here, for x equal to 1, I'll get y square is 1, which gives me that y could be plus or minus of 1. So what's happening over here is that that basic rule is getting violated. So for a certain value of x, for x equal to 1, you're getting two possible values of the output. So something like that is not allowed in the definition of a function. Okay? So again, one basic requirement for a relation between x and y to qualify as a function, where again we are assuming x to represent the independent variable and y to represent the dependent variable, and that condition is that for one specific value of, for any one value of x, the corresponding value of y must be unique, or in other words, for any value of the input, there should be exactly one output. Now, for the time being, and even for a large part of calculus, we'll be dealing with what are known as real valued functions. So for a real valued function, essentially, what we mean by a real valued function is that the input, the input will the input x will be restricting the input to real values, and the corresponding output also will be restricting to real values. Right? Now, in the context of functions, there are two terms which are very important. There's something known as the domain of a function, and there's something known as the range of a function. And again, we are specifically not talking about real functions and real valued functions, which means that the values that x can be given and the values that y can assume are restricted to the set of real numbers. So let's just look at these terms also. Now, under the condition, once you want that the function's input, in a lot of cases, depending on the structure of the function, once you impose this condition that the output of the function must be a real value, depending on the way the function has been defined, there might be certain restrictions that you might have to impose on x. So as a simple example, suppose I were to consider the function y equal to, again, 2x minus 1. So over here what's happening is that, and again the restriction is that x has to be a real value and y also has to be a real value. So specifically, x has to take only those values for which y will be a real value. Right? So now for y equal to 2x minus 1, what's happening is that if you think about it, those values of x for which y will be real, it's easy to see that x can take any possible real value. Because what's finally happening over here only is that you're taking a certain value, the input is x, you're multiplying it by 2, and what the function is essentially doing is it's taking the input x, multiplying it by 2 and subtracting 1 from it. So you have simple operations involved, and as such, for every real value of x, 2x minus 1 will also turn out to be some real value. So there is no issue over here. So over here I'll say that, even as long as, because you want to keep y as a real value, x can take every possible real value. There's no problem over here. But in this particular example, suppose I consider this function. Over here what you're doing is, the function is doing is, it is taking the input x, subtracting 1 from it, and then taking a reciprocal. Now over here, it is easy to see that x cannot take all possible real values. Right? And which is that value of x for which there will be a problem? That value clearly is 1. And that is because for x equal to 1, you will have something like 1 by 0, which is mathematically not defined. So mathematically, something, a ratio in which the numerator is non-zero and the denominator is 0, that will mathematically, we always say that is mathematically not defined. Something like 0 by 0 form is mathematically defined, but it turns out to be something known as an indeterminate form, which we'll be looking at later on. Right? That is also, when I say that 0 by 0 is an indeterminate form, that is in the context of limits, something approaching 0 upon something approaching 0. But something which is non-zero upon something which is exactly 0 will never be mathematically allowed. So as a result of that, now I'll say that over here, if you want to talk about real possible values of y, you'll obviously have to ensure that x does not take the value, assume the value 1. So as a result, for this particular function, there is a restriction that has now come up, and that is that the value of x should not be equal to 1, and every other value of x is allowed. Right? And similarly, now if I suppose talk about this function, the square root function. So over here now what I'll obviously say is that if you want y to be a real value, then the quantity under the square root should obviously not be a negative number, because if x is negative, then the square root of x will obviously be a non-real value, as we've discussed before when we looked at basic complex numbers. So over here I'll say that for y, if you want to ensure that y is real, you basically pretty much have to ensure that the value of x is greater than or equal to 0. So x should only take values over here which are greater than or equal to 0. So in all these three cases, these set of values that x can assume is basically referred to as the domain of the function. So whenever we talk about the domain of the function f of x, y equal to f of x, we are essentially referring to, this is in the context for a real valued function. So for the domain of a real valued function y equal to f of x is the set of values that x is allowed to, is the set of values that x or the independent variable can assume, right? And those set of values is basically which values x can assume or cannot assume is basically decided on the basis of, is essentially the largest set, such set is decided on the basis of the requirement that y must be real, right? So the domain again is the, as an example, so d subscript f over here refers to the domain of f(x). So for 2x minus 1, the domain is all real numbers. For 1 upon x minus 1, I'll say that x can take all real values except 1. And for root of x, I'll say that corresponding second important set is something known as the range. And the range is basically what to y, what the domain is to x. So now what will happen is that once you identify the domain of the function, that is the set of values that x can take, so what will start happening is that you can kind of think of a table of sorts. That, you know, maybe you have a table of this form in which you'll start kind of listing the values that x can take. And for each value of x, we've already seen that you'll get a corresponding unique value for y. So you'll start listing the value that y can take. So the range essentially will be the collection of all these values in the second column as x takes all values over its domain. So the range is essentially again the collection or the set of all possible values that the dependent variable, that is y, will assume as the independent variable, which is x, assumes all its values over its domain. Okay? Usually finding the range of a function is not as straightforward as finding the domain, so we won't get into too much detail right over here. Of course, in the chapter on functions, which we see later on, we'll be looking at different techniques that can be used in locating, in trying to identify the range of a given function. Let's just take some simple examples at this stage. So again, for y equal to 2x minus 1, we've already seen that the range domain happens to be the largest possible domain that we can take is the entire set of real numbers. Now for the range, again, what you want to figure out is that as x takes different real values, what are the kind of values that y will assume. So here again, it's easy to kind of imagine this, that as, again, what you're essentially doing is you kind of taking a value, multiplying it by 2 and subtracting 1 from it. So as x takes all possible real values, you can be pretty sure that the set of, that the variable y will also assume all possible real values. Another way in which the same thing can be thought of is that, suppose I rearrange terms over here. Over here, y essentially represents y represents a dependent variable over here. But I just rearrange terms over here to get it in this form. And the statement can be thought of in this way, so that what are the values of what real values can be assigned to y for which the corresponding value of x also turns out to be real. Right? So for example, in this it's easy to see that if you choose any specific value of y, you'll get a corresponding real value of x. And this will be true for all possible values of y. So the range, so I can kind of say that y itself can now take all possible real values, and for each value of y, you will get some corresponding unique value of x over here, right? So in this case, again, I'll say that the range is that y can take all possible real values. But on the other hand, now if we look at this example, y equal to x squared plus 1. Now for the function y equal to x square plus 1, again it's easy to see the domain can be taken as a set of all real values, because again finally you're squaring a value and adding 1 to it. So that operation will be defined for all possible real values. And as far as the range is concerned, we can use the fact that x square itself will always be greater than or equal to 0 for all x belonging to a set of real numbers, which will imply that x square plus 1 itself will always be greater than or equal to 1 for all x belonging to the set of real numbers. So in this case again it's very simple to see that as x takes all values from minus infinity to infinity, as x takes all possible real values, y will itself assume each real value which is greater than or equal to 1, and therefore I'll say that for the function y equal to x square plus 1, the range is the set 1 to infinity. So the range is the set of values of y such that y is greater than or equal to 1. And just one last concept with regards in the context of functions that you want to look at is something known as the range of, is something known as the graph of a function. Graphs are something which you are kind of familiar with from your junior standards also. So just through a simple example, we want to understand that what do you actually mean by the graph of some function y equal to f of x. So again, let's start with let's take a simple example. So suppose we consider this function y equal to x square plus 1. So again, as we've seen, what will happen in y equal to x square plus 1 is that x will take all real values from minus infinity to infinity, and y corresponding takes all values which are greater than or equal to 1. So what is really a graph? Graphs of a function essentially visually represent the relation between x and y. Or in other words, they visually capture give you a lot of information. So for example, they'll tell you something about the variation of y as x changes. So graphs can be very important in terms of the information that they contain. So intuitive way to understand graphs is as follows. So suppose again, we kind of come up with these two columns. So we'll start giving values to x and we'll start giving corresponding values to y. So although x can take every real value, let's just stick to simple values. So maybe let's say minus 2, minus 1, 0, 1, 2, 3. Of course, I'm just taking simple values. It's not that x can only take integral values. So now the corresponding values of y would be 5, 2, 1, and then again right. So I looked at it. I have these 5 specific values of the input, and I've got these 5 corresponding values for the output. Now what we can start doing is we can start constructing ordered pairs. Right. So an ordered pair again is something which is a collection of 2 elements, right? So the ordered pair x comma y will correspond to the collection of values of x and corresponding values of y. So over here, corresponding ordered pairs now become minus 2 comma 5. That's one. So now we'll essentially use the idea that an ordered pair, essentially every ordered pair of the form x comma y, where x and y themselves are real values, essentially corresponds to a point in the coordinate plane of the xy plane, something which you are familiar with. So the xy plane, as you've seen in basic graph plotting in junior standards, where you've plotted straight lines and things like that, on your graph paper. So the coordinate, the xy plane, essentially again, every point, every ordered pair x comma y, where x and y are real values, is essentially a point on that xy plane. So again, you have an infinite set of values of x, and you have these infinite set of values of y. Correspondingly, you have these infinite ordered pairs x comma y. All these infinite ordered pairs correspond to a collection of infinite points on the xy plane. So now, what is the graph of y equal to f of x? The graph of y equal to f of x will now be the curve. It will be that curve which happens to pass through all these points, right? So every point on the graph of I equal to f of x will be an ordered pair x comma y, which essentially will satisfy this particular relation, right? So if I say that a comma b is some point on the graph, then what must happen is that a comma b will satisfy this equation, which will mean that b is equal to a squared plus 1. So if I want to get a basic shape of what the graph looks like, all I have to do is plot these points. Of course, we can't plot infinite points, but just to get a basic idea of the graph, we'll just plot these 5 points. The more points that you plot, the more accurate your graph will be, obviously. So 1 point is 0, 1. So then that's over here. So you can just, if you want to make a simple scale, so 1 point is 0, 1. That's over here. Then you have 1, 2 and minus 1, 2. Then you have 2, 5 and minus 2, 5. And of course, you can keep plotting such points. But at least we're getting an idea of the basic shape that the graph will look like. So the graph has to pass through all these points then. So that's what the basic shape is looking like. The graph of y equal to x squared plus 1 would look something like this. Of course, if you want a more accurate graph, you'll kind of have to consider more points. But usually for us, we essentially just require the basic shape of the graph. Right? So some observation that can be clearly made is that this graph will turn out to be symmetric about the y-axis, which essentially means that the portion to the left of the y-axis and the portion to the right of the x-axis are kind of images of each other in the y-axis. Right? But, so again, the basic idea that we just wanted to understand was that, what do you mean by the graph of y equal to x? So again, one way to visualize it is that you have a certain set of values of x, you have corresponding set of values of y, you have corresponding ordered pairs x comma y. All these ordered pairs themselves correspond to points in the xy plane, and the graph will essentially be a curve which will pass through all these points. Now, in case of a function, we had talked about this, that a basic requirement for a relation between x and y to be a function is, again, assuming that x is the independent variable, is that for a certain value of x, you can only have exactly one corresponding value of y. But what that would mean geometrically now is that, if you have the graph of a certain function, what must necessarily happen is that if I were to draw a line parallel to the y-axis, once you draw a line parallel to the y-axis, you've basically fixed the value of x. Right? So once you fix the value of x, the corresponding value of y that you'll get should be unique, which means that that line will have to intersect this graph at exactly 1 point. So so the graph. So one basic requirement that the graph of y equal to f of x has to satisfy is that for any line drawn parallel to the y-axis, that line will intersect the graph at exactly 1 point. Right? If it is intersecting the graph at more than 1 point, then that graph will not correspond to then that graph cannot be the graph of a function. The last thing, again, in the context of function that I want to talk about is, which will be important for us, is that given the graph of a function, for a given value of the input, how will you geometrically locate the value of the output? So suppose this is the graph of some function y equal to f of x, and we're taking these 3 specific values of x, a, b, and c. Right? So the idea is that where is basically in this, if this is your graph, if this is x equal to a, again, how do so these are 3 possible values of the input. So this is y, and this is the value of the independent. So value of the independent variable, value of the dependent variable. So it's again a simple, straightforward idea. The value of the function at x equal to a, how will you obtain that value? You'll basically draw a line parallel to the y-axis through the point x equal to a. Given that this is a function, the graph of a function, that line will intersect the graph at exactly 1 point. Right? So through A again, draw a line parallel to the y-axis. Now, for this is a point. Let's denote that point as capital A, whose x coordinate happens to be small a. Right? But we've already seen that every point on the function, on the graph of the function, is an ordered pair, which will satisfy the equation, which will satisfy the relation between x and y. So if the x coordinate of this point is small a, the y coordinate will obviously have to be, the y coordinate will have to satisfy this relation. So if x is equal to small a, y will have to be f of small a. So f of a. Which means that the function value in this case represents the y coordinate of this particular point, which means it would represent this particular height along with the sign. So in this case, of course, in this specific case, I can also argue that f of a is some value which is definitely positive. Right? So this is important. So from the graph of a function, given a certain input, suppose a, f of a will basically, which is the value f of a, through x equal to a, you're drawing a line parallel to the y-axis. That line will intersect the graph at exactly 1 point, assuming that it's the graph of a function. The y-coordinate of that point of intersection is basically the function value, and the x-coordinate of that point is basically the input value, x value. Okay. Similarly, over here, I can draw a line through B parallel to the y-axis. This is my point of intersection, capital B. So coordinates of this point will be B, comma, f of B. So again, in this case, clearly f of B is a value which is negative. And finally, in this case, capital C, small. In this case, clearly, since this point is on the x-axis, the y-coordinate of this point must be 0. But the y-coordinate of this point should have been f of c. So that obviously means that the function value at c in this case is turning out to be 0. So again, so in this particular diagram, f of a is a value which is positive, f of b is a value which is negative, and f of c is a value which is 0. So just please go over this again once. So again, given an input value, if you want to find the corresponding value of the corresponding outer value geometrically, through x equal to a, you'll draw a line parallel to the y-axis. It'll intersect the graph at exactly 1 point. The coordinates of those point will, the coordinates of that point will essentially be a, comma, f of a. Right? Similarly, from the output value, if you want to get the input value, what will you do? You'll draw a line through the output. So if the output is 2, you'll draw a line parallel to the x-axis at a height of 2, at a height of plus 2, and you look at the corresponding points of intersection, and from those points you'll draw perpendiculars onto the x-axis. And last thing before we go to quadratic expressions is this a very basic idea associated with something known as a parabola. So a parabola is one of the second degree, one of the conic sections that we study in detail later on in coordinate geometry. But for the time being, we just want to look at something basic idea. We just want to look at what a parabola looks like. How is it? What does its shape happen to be? And a couple of terms associated with the parabola, right? So a parabola essentially would have a shape of which would look like something like this. Right? The dotted line, of course, is not a part of the parabola. So the parabola is this particular curve, and this, of course, is just a particular snapshot of the curve. The curve will keep extending. So the only thing that we want to know about a parabola for the timing is that a parabola first of all it's an open curve. By an open curve, by something which an example of a curve which is not open or a closed curve is a circle or an ellipse, right? But a parabola would be an open curve, which means that a parabola is an open curve, so it will keep expanding on both sides, right? And for every parabola, there's always a line of symmetry, which we refer to as the axis of the parabola, right? So every parabola will have a line about which the parabola is symmetric, and that line is called the axis of the parabola. So that is one important term that you need to remember. The second important term is something known as the vertex of a parabola. So the vertex of the parabola, the axis is a line which will intersect the parabola at exactly one point, and that point is basically referred to as the vertex, right? So again, the axis of the parabola is the line about which the parabola is symmetric, and the vertex is a point at which the axis will intersect the parabola. So in this case, the vertex is somewhere over here. Right, so this is the only thing that we're really defining for a parabola at the moment. Of course, later on, when we look at parabolas, under conic sections, we'll be looking at a lot of its properties. We'll be geometrically defining the curve. What is the parabola as a set of points, etc. And of course, we'll be looking at a lot of its properties also. But again, for the time being, in the context for quadratic expressions, these are the only two terms that we need to know. Something known as the axis of the parabola and something known as the vertex of the parabola, and of course it's an open curve, so as you keep going along the axis, the curve will keep expanding on both sides. So finally, after all this information, we can start now talking about quadratic expressions. So now the way we have defined polynomial equations, you can now start talking about polynomial functions. And a quadratic expression now basically becomes a polynomial function of degree 2. So a function of the form f of x equal to ax squared plus bx plus c, where again a, b, c belong to the set of real numbers and a is not equal to 0, is a quadratic expression, right? So again, any function of the form f of x equal to ax squared plus bx plus c, where a is not 0 and abc can take any real values, will be a quadratic expression. Now, what is important for us is to be able to plot the graph of quadratic expressions under different conditions. Okay. So for that, I'll state something without proof at this stage. Again, when we look at conic sections later on, we can prove all these points in detail. Right? And so the graph of any quadratic expression, so the graph of y equal to ax squared plus bx plus c, will always turn out to be a parabola whose axis happens to be parallel to the y-axis. Right? So now this gives us these possibilities in terms of the general shape. So let's just quickly look at all the possibilities. So suppose this is the x-axis. We're not plotting the y-axis for the time being. So I can have these situations. Plotting the y-axis for the time being. So I'm plotting we're considering different possible cases, the different possible scenarios with respect to the x-axis. This is the x-axis, and these are the 6 different possible scenarios. In each case, again, we just considered certain snapshots of the parabola. They keep extending up till infinity. So in each of the cases, you can see that the axis, if you were to draw the axis, given that this is the x-axis, the axis will be the axis of the parabolas of each of these 6 parabolas are perpendicular to the x-axis, which means that they are parallel to the y-axis. So the graph of any quadratic expression will always fall in one of these 6 categories. And of course, with respect to the y-axis also, the y-axis could be anywhere over here. So let's just label these cases. So 6 possible scenarios. So what is important for us, again from the point of view of quadratic inequalities and some other concepts, is to be able to identify, given the quadratic expression, given the values of a, b and c, it is important for us to be able to identify that exactly which of these 6 possible cases is, exactly which of these 6 cases is happening, right? So let's just quickly list those ideas now. right? So first of all, of course, there are, by observation, there are two broad cases. In cases 1, 2, and 3, the parabolas are opening up, and in cases 4, 5, 6, the parabolas are kind of opening down. So this turns out only depends on the sign of a, the sign of the coefficient of x squared. So it turns out that if a is positive, if the coefficient of x squared is positive, the parabola that you will get will always open up. So that will either be cases 1, 2, or 3. And similarly, if a is negative, the parabola will always open down, which is cases 4, 5, and 6. So 1, 2, and 3, in all of them, a of course is positive, but still how are we differentiating in the cases 1, 2, and 3? In 1, what is essentially happening is that the curve, the graph is not intersecting the x-axis at all. In 2, what is happening is that the curve is just touching the x-axis at one point, or effectively there is one point of intersection. And in the third case, the graph is intersecting the x-axis at two distinct points. So there are 2 points of intersection. So all of these cases now, so cases differentiating between 1, 2, and 3, it turns out will depend on the discriminant value b square minus 4ac. So first of all, one basic observation is that all the 3 cases, 1, 2, and 3, essentially differ with respect to the number of points of intersection of the graph with the x-axis. And if you want to talk about the points of intersection with the x-axis, you have to put y equal to 0. So to find, once I put y equal to 0, I'll get a quadratic in x. So what will now happen is that the roots of this quadratic will give us the points of intersection. Quadratic, and I solve it, and the roots turn out to be alpha and beta, then what we can say is that the roots, the points of intersection themselves are alpha comma 0 and beta comma 0. Obviously, these points of intersection will only exist if alpha and beta are themselves real. So again, if my roots turn out to be 2 comma 3, then that roots over here turn out to be 2 comma 3, that effectively would mean that the points of intersection are 2 comma 0 and 3 comma 0. If the roots turn out to be identical and are equal to 2, then I'll say that both the points of intersection are 2 comma 0, which will actually correspond to case 2 and or 5. And if the roots over here turn out to be non-real, then you'll say that effectively there are no real points of intersection. So the graph is not intersecting the x-axis at all, which is cases 1 or 6. So now it's easy to see how the whole thing depends on the discriminant. So for a quadratic expression, again, we can talk about the discriminant. And if that discriminant is negative, let's start with the positive case. If the discriminant is positive, there are 2 distinct points of intersection. So that is cases 3 and 4. That's one point of intersection, which is cases 2, 5. And discriminant negative basically means that 0 points of intersection. This is very important again from the point of view of solving inequalities. So whenever you want to impose a condition that the graph, whenever you want the graph intersects the x-axis at 2 distinct points, we'll say that the discriminant must be positive. If the graph only has to touch the x-axis at one point, you'll say that the discriminant is 0. And if the graph does not intersect the x-axis at all, you'll say that the discriminant should be negative. Right? Third very important point is that the coordinates of the vertex will always turn out to be at this particular point, minus b by 2a comma minus d by 4a. This is pretty important. So in all the cases, the x coordinate of the vertex is always going to be minus b by 2a, and the y coordinate of the vertex will always going to be is always going to be minus d by 4a, where d again is your discriminant. And one last and very simple idea is that the y-intercept of this parabola. Each of these parabolas will intersect the y-axis at exactly one point, and that point is given by 0 comma c. Y equal to x squared plus bx plus c was the equation of the curve, and if I put x equal to 0, I'll get y as c. So let's just quickly take some examples of some quadratic expressions and quickly plot them. Again, we are only interested in a rough plot of the expression. Right, so let's again quickly just plot the graph of these functions. For the time being, to plot the graphs, we'll of course be plotting them relative to the x and y axis both. Later on, when we use the idea of quadratic inequalities, when we use the idea of plotting the graph to solve a quadratic inequality, we'll be only interested in specifically the plot of the graph relative to the x-axis. So for each of them, of course, the first thing that you want to look at is whether it's a parabola opening up or down, and the second thing is what is the interaction with the x-axis. So in the first case, let's go to the discriminant. So the discriminant is 25 minus 24, so that's 1. So A is positive, so it's definitely opening up. Then the discriminant is positive, so it's definitely intersecting the x-axis at 2 distinct points. We would also like to find the points of intersection. So y equal to 0. So that gives us x as 2, 3. Once we get x as 2, 3, we also are interested in the vertex. So minus b by 2a. Minus b by 2a becomes 5 by 2. And minus b by 4a becomes minus 1 by 4. So looking at all this information now, so again it's opening up. Points of intersection are 2, 0 and 3, 0. So this is approximately what your graph looks like, 2, 0, 3, 0. In fact, this point also will be, for x equal to 0, you get y equal to 6. So this is again is a rough plot, it's not really to scale. And the vertex we've seen is 5 by 2, Let's just have a look at this. Again, this is a rough plot, and this is what we're interested in. The second one again is positive, and if you look at the discriminant, it's turning out to be 0. And again, if I put y equal to 0, I'm getting x as, it's actually 2x minus 3 whole square, so x is turning out to be 3 by 2. Right? The vertex again should be minus b by 2a, so that's 12 by 8, so that's 3 by 2, and d of course is 0, so minus d by 4 would be 0. So in this case, since d is 0, in fact, since d is 0, it's obviously, and it's a parabola opening up, and the discriminant is 0, so it's touching the x-axis at one point. And that point will obviously be the vertex. The point at which the parabola is touching the x-axis in this case will obviously be the vertex. So that's why the vertex is 3 by 2, 0. Again, if you want to talk about the point at which it intersects the y-axis, that should be 0, 9. And again, this is not to scale. Third one, again parabola opening up, but the discriminant now is 1 minus 4 equal to minus 3. Now the discriminant has turned out to be negative in this case, which obviously means that the parabola is not intersecting the x-axis at all, in which case you don't even have to find the points of intersection because they don't exist. So the vertex we would be interested in. So the vertex is again minus b by 2a, so that's minus 1 by 2, comma, minus d by 4a, so that's plus 3 by 4. Okay. So the vertex is at minus 1 by 2, comma, 3 by 4. And again, if you want to find this point, this point is 0, comma 4. Fourth one now, a is negative, so the parabola will open down. The discriminant will be 9 plus 16, so that is 25. So there are two distinct points of intersection. If I put y equal to 0, putting y equal to 0, we get the values of x as minus 4 comma 1, right? So the points of intersection therefore are minus 4 comma 0 and 1 comma 0. And the last thing, the vertex. Vertex again was at minus b by 2a. So now you just have to be careful. Minus of 3, minus of minus 2, so that's 3 by 2. So that's minus 3 by 2. Comma, minus d by 4. D itself is 25. So minus 25 by 4 times minus 1. So that's plus 25 by 4. Right, so the vertex is in the second quadrant and at x equal to 0 again minus 1. So this would be the approximate plot for the fourth function. Now in the last one, we we haven't been given specific values of a, b, and c. We've just been told, we've been given information about the signs. We'll still be able to figure out a rough plot for the function. First of all, again, we need to observe that a is definitely negative, so it's a parabola opening down. Now for the discriminant, if you observe, the discriminant is b square minus 4ac, right? So that's b square. So given that the discriminant is b square minus 4ac, and a and c, if you observe, are of opposite signs. So a is negative and c is positive. So a into c will obviously be negative, which means that minus 4ac as a term becomes positive. So this is b square plus minus 4ac. So b square is positive and minus 4ac is also positive. So the discriminant as a result is clearly, definitely going to be positive. Right. So so you have a parabola opening down and it's intersecting the x-axis at two distinct points. But another piece of information that we need is that where would the vertex be, right? So that can again easily be found out. As we know, the x-coordinate of the vertex is minus b by 2a. Now, b by 2a is clearly positive because a and b both are negative. But that would mean that minus b by 2a as a value must be negative. So since b and a have the same sign, b by 2a must be positive, but then as a consequence, minus b by 2a must be negative. Which means that and of course minus d by 4a, since d is positive, minus d by 4a remains. Right? D was positive and a is negative. So d by a is negative, so minus d by 4a is positive. So the vertex is actually in the second quadrant. Right? And so in the fifth question again, I can say that the graph will have to look like this particular. Will have to have this particular form. In the fifth question, if c had been given to be, if c was given as a negative value, then they would have been a certain ambiguity, because then there could have been different situations. If c had also been negative, then b square minus 4ac could have either been positive, it could have been 0, or it could have been negative. So there would have been three possibilities depending on the exact value of c. So first, if c had been given as a negative value over here, then we could not come up with there would have been different possibilities in that case.